Hello. So this is the first video for Unit 11, which is on liquids, solids, and solutions. So it's how those we're mainly going to be talking about today is how particles interact either in solution or like within liquid and solid states, okay? Unit 12 is all about gases. Gases behave very differently from liquids, solids, and solutions. These three states of matter, because solution in chemistry is like its own state of matter, these states of matter all have very similar properties, which is why they get lumped together, all right? So today we're going to be talking about intermolecular forces, all right? The board, what I'm going to be showing up here is going to look slightly different from your packet. The information's all the same, it's just I had like retyped it into a nicer thing, and what I have up here on the Promethean is going to look a little bit different. But it's the same stuff. Okay? So, just to recall, you know, from the stuff you learned in Unit 10, an intramolecular force is a force that is within the molecule, okay? It's a fancy word for bond. It's a fancy word for bond, okay? So it's the forces that hold an intramolecular force, or bond, is what holds atoms together within the molecule. And there's multiple types: ionic, covalent, metallic, which was all reviewed in Unit 10. And if we're talking about covalent, molecules are formed by sharing electrons between the atoms, so that's covalent. Or if it's ionic, then they're being transferred. We're mainly going to be talking about covalent today. All right. So these are intermolecular forces. Okay, these are forces that occur between molecules. And there's two main types, and one of those has a subtype. Okay, there's dipole-dipole forces, and then there's London dispersion forces. Within dipole-dipole, there's also hydrogen bonding, which is a strong type of dipole-dipole. And these are all going to be things we're going to review today. And just an FYI, intramolecular bonds, like ionic, covalent, metallic, are all stronger than intermolecular forces, which is why if I took a cup of water and I put it on the stove and I started heating it, it's going to boil, which is overcoming those intermolecular forces holding the molecules together before I would actually decompose the water molecule into hydrogen and oxygen. Okay? The amount to break a bond is a lot more energy than to overcome a force holding molecules together. Okay? Or think about it this way. You see a couple dating. The amount to break them up is a lot less, the amount of energy to break them up is a lot less than to like break one of them in half. Okay? So, intramolecular bonds, no, we're not going to test it. Ionic, covalent, metallic, that's like what holds you together. And then like intermolecular force is like the relationship between you and another person. Okay? All right. Not to get morbid. All right, so hydrogen bonding. So I talked about water before. Shh. I talked about water before. Your diagram is not colorful like this one is, but these blue dotted lines within here, those are my intermolecular forces. This is a hydrogen bond, which I know it has the word bond in it, but remember that's just a force. And then within the molecule, like this right here, is my covalent bond. Again, if I were heating this, the energy going in would first be to overcome the forces holding the molecules together, to overcome those hydrogen bonds. I would have to add in a lot more energy, and oftentimes electricity needs to be added in to actually break the covalent bonds holding the oxygen to the hydrogens. Okay? All right. So, phase changes. Phase changes, if you recall from Chem 1, All phase changes are physical changes, and that is because you're overcoming intermolecular forces. Okay? So when a substance changes from solid to liquid to gas, the molecules themselves remain intact. You're not changing what the molecule is, you're just changing what it's attached to. Okay? Or what it's interacting with. Like I already said, they're due to those changes in state are due to the changes in forces among the molecules rather than those within the molecules. When phases change, intermolecular forces are overcome. Okay? Between these three images here, which one of these do you think is experiencing the most intermolecular forces? The solid. And in the liquid phase, they're still experiencing quite a lot. They're just a little bit weakened from the solid to the liquid. They're just a little bit weakened. They're like loosened. It's like solid is before you stretch and liquid is after you stretch. Right? They're just a little looser. And then gas, they're barely experiencing intermolecular forces. And when we do Unit 12, when you watch those videos, you'll see that they barely, like the amount that they experience is considered to be negligible. Okay? All right. So now let's talk about the three main types of intermolecular forces. And actually, this next thing, this image on the next page goes through even ionic stuff, which I'll talk about a little bit today. We'll talk more at a later class. We good here? All right. So, when trying to determine if we have interacting molecules or ions, we could talk about ions interacting as well. First of all, if ions are not involved, then we're mainly going to be talking about what types of compounds? Covalent. All right, so looking at this left side, this is all for covalent, okay? If there are polar molecules involved, so that's your next question. If there are not, then it's the dispersion forces only, so LDFs only, okay? And we'll talk about in a little bit specifics about those, but LDFs only. If there are polar molecules involved, then it's dipole-dipole. If there is a hydrogen atom bonded to nitrogen, oxygen, or fluorine, then the type of dipole-dipole force it is hydrogen bonding. So it's kind of like a little flow chart. Now, these van der Waals forces, these three, dispersion, London dispersion, dipole-dipole, and hydrogen bonding, are all called van der Waals forces. This is what holds covalent molecules to each other. If there were ions involved, you could have an ion with a polar molecule, which is called an ion dipole force, which is like how ionic compounds dissolve in water. Because you have a polar molecule, like water, interacting with the positive and negative ions. And we'll talk about that when we talk about solution formation a little bit more. Okay? And then if it's just ions, like just ionic compounds, that is a later section. That's like what holds ionic compounds together. That's ionic bonding. Okay? And actually, section 8.2, that was unit 10. So that's like electrostatic forces. And we're going to talk a little bit more about that as well during this unit. Okay? Unit 10 was mainly the Lewis structures and stuff like that and the types of bonding. Unit 11, we're going to be talking about how those molecules like come together. Big picture. Okay? We good here? I wrote one word, so I think you're good. All right, so London dispersion forces, that's the first one I want to talk about. London dispersion forces. So in a London dispersion force, what is happening? Now remember, this actually something I want to highlight. And I don't know why that says including nonpolar. I feel like it should say including polar. These occur in all molecules, in all covalent molecules. If the molecule has electrons, then it'll experience London dispersion forces. Because the way London dispersion forces work is the electrons in the molecule, are they stationary or are they moving? They're moving. They're constantly moving. Those electrons are constantly moving. And what happens is what's called induced or instantaneous dipole. They occur accidentally. So for example, I feel like I have an image later. That's not a very good one. Find the right page. Okay, I don't like that one. Okay. So, for example, in the hydrogen atom, we're in the hydrogen molecule, H2. That is a covalent bond, right? How many electrons are there? 2. There's 2 electrons in that bond. Hydrogen doesn't have any more. And then there's another hydrogen molecule coming up near it, okay? Those 2 electrons in this hydrogen molecule, while they are being shared equally, they are not always going to be evenly distributed about both atoms within that hydrogen molecule. There will be times when there are more hanging around one of the atoms or the other. And in those instances, which is why it's called an instantaneous dipole, in those instances when the electrons are more towards one atom than the other, we get this temporary dipole, where one of the atoms has more electrons around it than the other, so that atom that has more electrons has a slightly more negative partial charge. And we talked about partial charges in Unit 10. All right? And so what ends up happening is with we have a temporary partial charge. Remember, that's a lowercase delta. I talked about that in the Unit 10 videos. That's a lowercase delta. It signifies a partial charge. And then this one would be partially positive. But that's temporary. I'm going to put that in parentheses because that's not all the time. All right, that's temporary. And then this other hydrogen molecule that might be near it, now what types of charges attract? Opposites or similar? Opposites. So if this one's partially negative, then that's going to force the electrons in this molecule to go more towards this hydrogen, making this partially positive for a little bit, and this one partially negative for a little bit, and then it kind of goes back. But it's like instantaneous, and it kind of sets off a chain reaction, but it's like happening all across all the molecules. But they're instantaneous, and they're temporary, and they're very, very fast. These changes in these partial charges, because the electrons are constantly moving. That's what holds them together, are these kind of like temporary magnets. Okay? Very, very weak. Very weak. Which is why typically nonpolar molecules are going to be in the gas phase. Because what's holding them together aren't very strong forces. The larger the molecule is, the stronger the forces, because you have more electrons. The more electrons in the molecule, the more chances for these instantaneous dipoles. Not changes, chances. And the reason these occur in all molecules is because all molecules have these electrons. Just in polar molecules, dipole-dipole or hydrogen bonding are the more significant force because they're much stronger. But we're going to do some examples where London dispersion forces still play a role in polar molecules. And you'll see what I mean. Okay? All right. Next one I want to talk about are dipole-dipole forces. So this occurs within polar molecules. This is where we have a polar molecule. Remember, a polar molecule has a permanent dipole. Okay, like water or HCl or something like that. We'll talk about HCl. Chlorine is more electronegative than hydrogen. So chlorine has a permanent partially negative charge, and hydrogen has a permanent partially positive charge. And remember, they're only partial because it's still a covalent bond. The electrons are being shared unequally there. Chlorine is kind of hogging them more than the hydrogen. Whereas in an ionic bond, remember those electrons, they completely separate, the ions completely separate, the electrons are completely transferred, and that's where you get the full charges. So covalent, polar covalent get the partial charges. So we have a dipole towards the chlorine. The chlorines are hogging that chlorine's hogging the electrons more. But because it's permanent, another HCl molecule will interact in a way that, again, opposites attract, and they're going to arrange themselves so that the hydrogens of one molecule are near the chlorines of another. Okay? And this is going to be stronger than LDFs, stronger than London dispersion because it's a permanent dipole. It's not changing. Yep, it has to do with electronegativity differences, which we reviewed in Unit 10. That's just what a dipole looks like. Remember from Unit 10? Yeah, that's just the way that the arrow goes. It just means dipole. All right. But if you look at this last point here, while these are stronger than intermolecular forces, they're still extremely weak when compared to bonds, like covalent and ionic bonds. They're still extremely weak when compared to the actual bonds. All right? Now, hydrogen bonding occurs the same way as dipole-dipole because it is a type of dipole-dipole. It's just an extra strong type. All right? You have to have hydrogen bonded to nitrogen, oxygen, or fluorine within the molecule, right? Because you have to create a much larger electronegativity difference. So the dipole is just stronger.
So like
Water, hydrogen, yeah, like, so H2O, HF, NH3, and then any of the organic compounds that have OH groups on it, like ethanol. Any molecule where oxygen is bonded to hydrogen, nitrogen is bonded to hydrogen, or fluorine is bonded to hydrogen. You have to have that, okay? But the way it occurs is like the same as dipole-dipole, so I'm not going to redraw all that stuff. And plus, you have the image back here with water. Those were all hydrogen bonding. Okay. All right. Oops. There we go. Okay. So looking here, top of page 3. So in general, the stronger those intermolecular forces are, the greater the melting and boiling points. Remember, melting point is the temperature at which a substance melts. Boiling point is the temperature at which a substance boils. So typically, the stronger the intermolecular forces, the higher the melting and boiling points. So looking here at this graph, we're comparing a bunch of different molecules. Notice H2O, HF, and NH3 are 3 of the substances on this graph, and they have the highest melting point. Why is that? Because they all experience hydrogen bonding. They all experience hydrogen bonding. But then, like looking at this very bottom line, the CH4, SiH4, GeH4, and SnH4, those are all substances with hydrogen. Those are all nonpolar. But notice how it generally is increasing the boiling point as we go up because the number of electrons are increasing. Because that's London dispersion forces, number of electrons. So yeah, as you increase the period, so you have number of electrons increasing. Okay? So looking at our first, no, okay, I'm not going to go through that. I meant to actually delete that. Okay. This is exercise 1. This is exercise 2. Okay. Again, yours is just in a slightly different arrangement. All right, exercise 1. Which molecule is capable of forming stronger intermolecular forces, N2 or H2O? And then we're going to explain. So what do we think? H2O, for sure. And why? Because it experiences hydrogen bonding. So for questions like this, which I know I talked about when we were doing our last few problems for Unit 9, whenever it's a comparison question, you always need to reference both things. All right? We wouldn't just say H2O because it experiences hydrogen bonding. We need to say N2 experiences London dispersion forces only. H2O experiences hydrogen bonding, which are stronger than London dispersion forces. And you could say something, you guys have more room on your page, but you could say something like hydrogen bonding because it's polar with H bonded to O. And you might draw the structures, something like that. N2 is nonpolar, things like that. All right, so make sure you mention both substances. All right. So for number 2, I'm just going to draw the 2 Lewis structures that I want us to look at for this formula. So C2H6O. So the first one we're going to look at is going to look like this. H. I'll even put lone pairs on the oxygen, even though it's not going to make a difference. And then our second formula is going to look like this. All right. We are going to do an organic unit after the AP exam, so this is a little preview to that. This one is called ethanol. This is an alcohol group. You might know that from biology, but an OH is an alcohol group. And then this, does anyone know what this one's called? I don't know. I don't teach it. No, carboxylic acid has to have, it would be like a double bonded to O and then an OH. This is an ether. This is called dimethyl ether. This is dimethyl ether. All right, so which one of these do we think would have the higher boiling point? Why? Good. And what type of bonding, or not bonding, what type of intermolecular force is occurring within dimethyl ether? Both of them are experiencing London dispersion. This one's dipole-dipole. I'm pretty sure this is polar because of that oxygen. Yeah. Because the shape of it would actually be bent at the oxygen. So it would be polar. Those lone pairs make it polar. So this one has hydrogen bonding. The strongest intermolecular force that it experiences is hydrogen bonding, whereas here, the strongest is dipole-dipole. Therefore, ethanol has the higher boiling point than dimethyl ether. I'm just letting you know, which is why we're doing the organic unit after the AP exam, because you don't need to know names of organic stuff. But a lot of you will go on to take organic chemistry in college, and so I want to give you guys a little bit of a boost.
Wait, so we don't have to draw these diagrams either, right?
You might have to draw them. But now that you've done Unit 10, you should have been able to do that. I just wanted to save time. All right. Number 3. Number 3. This is a Unit 12 question, so we're going to skip it for right now. But when we come back, when we do Unit 12, we'll talk about how intermolecular forces come into play with ideal versus non-ideal gases, ideal versus real gases. So this is a Unit 12 question. So we're going to skip on to number 4. Oh, hey, look, this one actually is in the same format as yours. Yay. All right. So we have the various types of intermolecular attractive forces. So looking back at that flow chart on page 2, we're basically choosing one of the bottom boxes. Okay? So yes, for right now, we've only really talked about covalent stuff, but keep in mind ionic stuff, okay? So for A, CH3OH, which type of intermolecular force do you think is occurring here? The hydrogen bonding? Anything else? And London dispersion forces. When it's hydrogen bonding, you do not need to state that it's also dipole-dipole because hydrogen bonding is a type of dipole-dipole. Okay? It's like a more specific type it's like saying all rectangles, no, all squares are rectangles, but not all rectangles are squares. Isn't that the saying? All of the ones that are covalent. So LDFs, remember, LDFs occur in all covalent molecules. What do they not occur in? Ionic. Good. All right. XE. What would hold a sample of liquid xenon together? LDFs only. So LDF is not only for covalent molecules, but it's also going to be for nonmetal atoms. Okay? And that we're going to talk about next class more. Okay? What about H2S? Which, okay, H2S looks like this. So use your knowledge of Unit 10. Is that polar or nonpolar, first of all? Polar. So what type of forces? Dipole-dipole and LDF. But the dipole-dipole is going to be the stronger, the more influential force there. Yes. CLF. That's an L, not an I. CLF. It would be dipole-dipole because fluorine, that's a polar bond. Fluorine is much more electronegative than chlorine, or that difference is like 0.5. So it is a polar bond. It's a slightly polar, but polar bond. So this would be dipole-dipole. Anything else? And London dispersion forces. All right, what about E? It's just ionic bonding. And we'll learn next class that what holds them together, and we talked about this before, this is electrostatic attraction. Okay, but we'll talk about that more next class as well. Okay. All right, just a little bit more, and then we'll be done. Ready? Okay. All right, so last problem, and then we'll talk a little bit more about how these forces influence things. For each of the following pairs of substances, predict which will have the higher melting point and indicate why. Oh, one thing, let me go back real quick. This one, this was page 2. The bottom row of this is increasing strength towards the right. Because when we were talking about the types of van der Waals forces, we talked about the strength, but we didn't really compare we didn't say how that compared with ionic, but moving to the right is increasing strength. Where was I? Here I was. Okay. All right, what do we think for A? CuBr2, and yep, so I'm not going to write out all the words, but this one has ionic. What's the force that holds Br2s together? LDS. And then ionic is stronger than LDS. Great. Awesome. CO2 versus SiO2. These are both nonpolar molecules. What do you think? They're both nonpolar. So remember, when you increase, for nonpolar molecules, how do you increase the strength of the London dispersion force? More electrons. So it would be SiO2, but it's actually not because it's London dispersion forces. I've been lying to you. Yes, SiO2 is nonpolar, but next class, after spring break, next class, we're going to talk about how this does something called a covalent network. And this is just a covalent molecule. SiO2. It is SiO2, even with your thinking, but it's not just because of London dispersion forces. SiO2 does something special, and we'll talk about that when we talk about the types of solids. It's kind of like a lattice, but it's instead of ionic lattice, it's a covalent lattice. All right, sulfur or chromium? Which one do we think would take more energy to melt? Why chromium? What? Somebody said it over here. It's a metal. Chromium is a metal, sulfur is a non-metal. And metals typically have higher melting points, okay? And again, we'll talk about that next time. So it's kind of like a little preview into next time. All right. And this last one. Has to do with lattice energy, which is that POGL we were supposed to do today. No, we are. It will be, it should be, No, I think this one would be, no wait, I think it would be this one. Because of lattice energy. So remember, lattice energy is QQ over R. Yes, remember, it's Coulomb's law, which I did go over that in the unit 10. Okay. Yes, there's a proportionality. Guys, in the unit 10 stuff that you've already learned, I talked about how the proportionality constant doesn't matter here. So it reduces down to QQ over R. So just make sure you rewatch those videos to refresh your memory on that. Okay, for those of you watching this video right now, they haven't actually watched those videos because I'm jumping ahead. All right. So last little bit, you can read through this. You can read through this. This is just how intermolecular forces influence things like surface tension, something called capillary action, and viscosity. So surface tension is essentially the resistance of a liquid. I lost my packet for a moment. The resistance of a liquid to increase its surface area. So typically, liquids with large intermolecular forces or strong intermolecular forces have high surface tensions. Okay? Capillary action is the spontaneous rising of a liquid in a narrow tube. There are things called cohesive forces and adhesive forces at play here, which we'll see on the next page in my images. For you, it's just at the bottom of that page. But cohesive forces is having to do with when the intermolecular forces among the molecules are stronger than the interactions between the molecule and like the glass. Okay, and this will make more sense when I show the images, so I'm going to skip over that for right now. And viscosity is the measure of a liquid's resistance to flow. So liquids with large intermolecular forces or molecular complexity tend to be highly viscous. So the weak, like syrup. That's a pretty complex substance or molecule there. I don't think it matters. So, So the weaker the intermolecular forces, the more flow will occur because those particles are not held together easily. So they're going to flow across each other a lot more. Like oil is fairly, it's not very viscous. It's going to flow very easily. Because what holds oil molecules together is just London dispersion forces. So they overcome pretty quickly as they flow past each other. Okay, when they're interacting pretty strongly, they're not going to flow as much because they want to stay together. All right, so let's talk about this capillary action, the cohesive and adhesive. So these images here. So you have the answers already. You have to circle them on your page. And this convex meniscus. So this would be a nonpolar liquid in a glass tube. Okay, glass is made up of silicon dioxide. Glass has polar ends to it. No. Not quite. I didn't say magnetic ends, I said polar ends. So this is liquid mercury here, okay? Mercury is mercury is one of those weird things. Even though it's a metal, it experiences it's kind of like nonpolar. It's a weird metal. So it is going to pull away from the glass because it'd rather interact with itself than with the glass. So that's why it's cohesive forces, meaning that they'd like to stay together more than adhere to the side of the glass, which is why mercury in a tube is going to have a convex meniscus. It's going to bubble up. Water in a tube, it's a concave meniscus because it wants to interact with the glass. So the interaction between the water and the glass is going to be stronger than the interaction of the water and itself. So this doesn't really have anything to do with strength of intermolecular force. It more has to do with type of intermolecular force. Okay? And what it's going through. If somehow we were able to make a tube out of some sort of nonpolar substance, I don't know what we could that would actually make a tube like this, like a straw, but the water would actually form a convex meniscus like mercury does in a glass tube. Okay? So it has to do with type of intermolecular force. So adhesive forces here. They want to adhere to the side of the glass. All right? So a lot of preview into next unit and a lot of referencing last unit.